Thank you, thank you for the invitation. And sorry I was not able to make it. I didn't know what I got in Hong Kong last week. But yeah, I'm stuck. So today I will talk about some recent work we have done in Moire materials, especially trying to understand the emergence of fractional chain insulators in rhombohedral graphene. But before that, oops, yeah, sorry. For people that are not aware of, Mark Kerbick, who was one of my collaborators and a well-known condensed matter theorist, passed away last week at a rather young age of 50. So Mark had many contributions in condensed matter, in fractional quantum Moore effect, graphene diostomatic field, Dirac materials, and more topological phases. And if you know, or if you knew Mark, you know that we will miss him a lot because he was bringing like lots of fun and joy at any workshop and conferences. But show must go on. So let me acknowledge my collaborators and the people that actually did the work I will show you today. So I would like to emphasize the role of these four people here. Jabin, who gave a talk, I guess, yesterday. Yves Kwan, who is now a faculty at University of Dallas. Jonah Herzog-Arbeitman, a PhD student that will graduate next year. And Aishu Lee, a postdoc in San Sebastian. I also briefly mentioned some more recent work we have done with Go Pichanda and Yi Zhang on database of 2D materials. Right. So a brief reminder about fractional chain insulators. I'm sure that most of you know the story, but you can date back at the question like, can we get quantum Morley effects in general, both the integer and the fractional, without any external magnetic field, and potentially at higher temperature? For the non-interacting case, the question was answered by Haldane in '88. So as long as you have a band with a non-zero Chen number, well, this will act basically like a single Landau level. And this will arise solely from the band structure, not from the extramagnetic field. The quantum Hall effect was first observed more than 10 years ago, and you have a very nice quantization, for example, here at zero field of the Hall conductance in red. And this is without applying any extramagnetic field. And it has actually a concrete application for people that want to build a quantum resistance standard that you can access in a lab without relying on high magnetic field. So that's the case for the integer quantum Hall effect, but you might wonder, what about the fractional one? If you think about the picture that you have from Landau level, what you would expect is, well, first you need non-trivial bands. You need them to be flat, so at least the flatness compared to the typical interaction strength, and well isolated from the other band, like Landau level are separated from each other, one from another, by the cyclotron energy. So before turning into the recent experimental results, let me give a brief history of the fractional chain insulators. You can trace it back to the story of fractional quantum effect in spin system by Kalmayer and Laughlin, the late 80s, or the interplay between fractional quantum effect and lattices by Cohen Reed, the early 90s. Early 2000, there was also a push in the quantum community to realize fractional quantum physics. And since they are dealing with neutral atoms, of course, the coupling with the magnetic field is not obvious. So lattice realization was also envisioned there as a way to get into the FQH regime, like typically what you would get in creating an Hofstadter model. And in the early 2010, a few papers use simple lattice models to numerically show evidence of fractional chain insulators with mostly relying on finite size numerics. 2 years ago, we had several experimental groups that used twisted MOT2, where for the first time FCIs have been observed. And twisted MOT2 is roughly like the prototypical example of an ideal FCI setup. So once again, you have 2 layers of MOT2 that you twist one compared to the other. The twist angle might vary between 2 degrees and 4 degrees. Not all angles will have FCI merging, but let's say the most prominent case is around 3.7 degrees. There are many groups that try to do TFT calculation to get the band structure of the twisted MOT2. Maybe I can focus on this figure here, which is where we have relaxation and spin-orbit coupling. And you will see that you have a top valence band which has a non-zero Chern number, typically it's equal 1, well separated by a gap from the first remote band, which, depending on the angle, we have a Chern number -1, typically when you are at 3.7 degrees, but might switch to another Chern value if you go to lower angle. So that sounds like the best setup. Just one word for twisted MOT2, the valley and the spin degree of freedom are log. So you can think about being in valley K as spin up and in valley K prime as spin down. So that's the actual measurement for the integer case, and here for the fractional one. And what is really amazing is not only to observe, of course, at zero field, as you can see here, but let's say for the integer case, it's still observed up to pretty high temperature, typically up to 8 Kelvin, even though the samples are not really clean. It's even worse than what we had back in the days when people have observed the fractional Mole effect in terms of mobility. So this raised the question, like, do we have FCIs everywhere as soon as we are in such a setup? So if you have one isolated Chern band, you might wonder in which case do we get, let's say, the analog of the Laughlin state at 1/3. So there is always a question of the competition between the kinetic energy and the interaction. And we know that this can lead to different phases. The typical example, if I kill the interaction completely, then I expect to have a Fermi liquid. It's basically the non-interacting limit. Or I can have a Chernowski wave. But at least if the interaction is strong, it sounds that most of the time we will get an FCI. So people have tried to make contact between the fractional translators and the lowest Landau physics. It has been studied in different names depending on your religion. It's ideal Chern band, flexible band, generalized Landau level. But they all cover the same idea. So it's some kind of generalization of a Landau level when you have a non-uniform magnetic field and a non-uniform metric. These are very nice frameworks in the sense that these frameworks allow you to obtain some semi-analytical results, but it's not a requirement. So we have, for example, time lattice models which are far away from this limit and they still exhibit fractional insulators. And it raised the question whether it's possible to really infer the emergence of an FCI just based on information coming from the one-body physics, be it the Berry curvature or the quantum geometry. And overall, the message here is that FCI is actually quite robust phases, especially if you're in that limit where the interaction is strong compared to the bandwidth and you don't care about band mixing. So now if you go back to twisted MOT2, yes, it's close to the ideal case, but maybe I think Javin said a few words about that yesterday. You have to be slightly careful. So if you want to reproduce the full range of experimental results, like why you have some FCIs and why some other that should appear due, for example, to some symmetries are not there, you have to take into account several factors. There is a crucial rule of band mixing, for example, that explains that why you have normatization at the filling factor -4/3, and also the parameters of the TFT model. So, for example, if depending on the how accurate is your DFT, your single particle model, you will not be able to see the charge density wave that is observed experimentally. But overall, right now, I think we have a pretty good description or understanding of what's going on for this system. Just to mention briefly, we can try to push a bit more the comparison between the theoretical result and the experimental one. There is some recent paper, experimental one, trying to measure the gap of the FCI. It's a story which is a bit more complicated. Basically, this is what you have here. So it's extracting the gap with transport measurements and by also adding some magnetic field. And basically, the notional resistance requires two gaps to capture what is measured experimentally. One that will depend on some spin degree of freedom and the bare FCI gap. And you can try to capture these gaps also from numerical results. It's not completely trivial, and we know quite well for the fractional quantum Moore effect, where we have like 30 years of history trying to extract from numerical results the experimental gap, and we know there is always a discrepancy by a factor typically of 2. But also something I would like to point out, the question where are the differences between FCI and FQH. In FCIs, for example, the anions can have dispersion. For the pure fractional quantum Moore effect, you can show by symmetry that the anions are without any dispersion, but it's not the case here. And also, would like to emphasize the dispersion that you obtain is really an effect of the interaction. So you can take, for example, the twisted T2 model and make the band perfectly flat. You will still have a dispersion for the anions. There's lots of discussion these days about, since you have dispersion for the anions, what about superconductivity and so on. But that's at least one major difference between FCI and FQH. All right, so that was the situation for the twisted T2. Now, let's move to the case of ombrage graphene, more precisely pentalayer. So you might have already seen that the slide about the result from the group of Longzhu. So the setup is the following. You have a stack of ombrage graphene with 2 HBN substrate. One of the HBN substrate will be aligned with a small twist angle compared to the graphene. And you will see different fractions, so measure different fraction, typically minus at 2/3, 3/5, and 2/5. So in a simple picture of the ombrage graphene, first break the inversion symmetry. You have different type of inequivalent stacking for the HBN substrate, which are rated by rotation. And when you look at the low energy electrons, so typically what you have here, they will be localized either at the top surface of the stack of graphene or at the bottom surface. As I mentioned, one of the HBN is aligned with a small twist angle. So you have a mismatch coming from the lattice between HBN and graphene and also the twist angle. So we can play the same game like in other Moire materials, so having a continuum model that we describe the low energy physics. A powerful knob, of course, of all these Moire material is the fact that we can apply, we can dope through gates, and we can also have a displacement field. So the displacement field here, call it T, or we use also notation V, will basically split the conduction band and the valence band. So naively speaking, in this model, if you do the calculation, you will have a large separation between the conduction band here and the valence band here. The conduction band will be localized on the top layer, whereas the valence band will be top valence band will be localized close to the bottom layer, which is the one where you have the aligned HBN. And the aligned HBN is very important to observe the FCI. If it's not aligned, you don't get any FCI. So it's a bit counterintuitive because what you measure in terms of FCIs is the physics of the conduction band. But the effect of the Moire, naively speaking, you expect to be maximal for the state which are close to the HBN substrate. So that's the relation between what we will use as V and T, the displacement field. And as I mentioned, the physics is in the conduction band. And as you see, the gap are almost zero between the flat band that you have here and the dispersive band. So it can be the simple picture or analog of the simple picture I was showing for a twisted MOT T2. Already there, you need to take into account more than one band. So there is a non-trivial question how we take into account the interaction, and it's actually related to the way we think about the effect of the Moire. You can define the interaction to be such that if you put your Fermi energy in the gap, the band structure, then the interaction should be zero. It's basically forgetting about completely the field valence band. The other one is to take into account the effect of the field valence band. And if you look at the electronic density coming from the field valence band, you see that there's strong imprint of the Moire. So in this average scheme, which emphasizes the role of the Moire, basically it's like a capacitor of where the valence band states, which have the imprint of the Moire, will act on the conduction states, which are on the top of the graphene stack. So before diving into the fractional case, let's start with the integer one. It has been studied by several groups. Of course, it will depend on the type of stacking. And the take-home message is it will depend on the type of stacking, it will depend on how you take into account the interaction, either in the average scheme where the Moire has a strong effect, or where if you take the charge-rate scheme where the Moire is less important. That's the phase diagram for different channel numbers, and basically channel number 1 is in purple. Let me emphasize that compared to the usual situation, for Hartree-Fock calculation, the results exhibit strong finite size effect, and it also depends a lot on which models you use for your continuum model. So the situation is already pretty complicated for the integer case. So there is now a question, okay, let's say you have the right parameters to describe the integer case. What about the fractional one? So you will see different attempts in the literature. The first one is to say, well, it's going to be difficult to numerically deal with 3 bands. So let's start with the Hartree-Fock calculation at numerical 1, which basically gave us this Hartree-Fock band structure. And here you see that you have a well-isolated chain 1 band. And let's project the interaction onto this chain 1 band and explore the emergence of FCIs. And if you do that, this is for 24 sites at filling factor 1/3 and 2/3. You have for the energy spectrum as a function of the momentum 3 low energy states, which is the typical first signature that you expect for an FCI. It's not the smoking gun of an FCI, but it's a requirement. And you see that for both fraction 1/3 and 2/3. Of course, in experiment, they only observe 2/3. So that's already like a signal that something might be off, but you could say, look, at 1/3, you're close to the band edge, or they have prime with the contact, so that's why they don't observe 1/3 yet. But so that's, you also observe it for very small system size. So 12 sites will be like 4 particles, and you still get an FCI. So very few finite size effect in this model. Now, if you know a little bit about fractional quantum effect, you know that in a single Landau level, there is an exact particle-hole symmetry that relates 2/3 and 1/3. For FCI, it's just an approximate symmetry, but here it's almost there. So once again, it will tend to say that if you have 2/3, you should get also 1/3. Is it surprising? I mean, after what I say during the introduction, not really. If your band is not completely crazy, and if your interaction is large compared to the bandwidth, and you don't have, here they don't take into account the remote bands, then there's a high chance you will get an FCI. So we need to include more bands to see if these FCI will survive once you go back to the full-fledged system. So unfortunately, since we will rely on exact diagonalization, there is a cap on what we are able to do. So for the time being, we will focus only on 3 bands. So that's the 3 conduction bands that I will consider. And I will solely focus on the filling factor 2/3 and 1/3. If you look at 2/3, the most that you can do with a faithful calculation, easy calculation with 3 bands is like 12 unit cell. So it's a tiny system. So the idea was the following. We can use the base, the one-body bases that come from a single particle Hamiltonian. But if you do a Hartree-Fock calculation in 3-band, basically it's just a basis transformation where you expect that the low, you will label your state from the most important one to create the churn 1 band, and 2 other states will be higher in energy. But it's just a basis transformation. So in principle, you can work in the Hartree-Fock basis or the original basis. They should give you exactly the same result. Where it starts deviating from being equivalent from the original basis and the Hartree-Fock basis is as soon as you truncate your many-body Hilbert space. Since we want to go to bigger system sizes than 12 unit cells, what we have to do is to either limit or cap the number of particles we have in the remote band, and remove some states, one-body states which are very high in energy, because we assume that they will not contribute much. And if you do this kind of approximation, of course, now the Hartree-Fock basis and the original basis are not strictly equivalent. But at least it's a perturbative method that you can improve like step by step by relaxing the truncation and seeing if you converge to some results. So let's start with the charge scheme. So the scheme with the way you deal with interaction where the Moire doesn't matter much. That's the calculation if you do like a single band, which is basically the approximation where you do not allow for any particles in the remote band. And you see that where we reverted the calculation, we get the same state. It was low energy physics at 2/3. But now if you start adding band mixing, so let me just explain this notation. So the 0, 0 or 1, 0 means that you allow for 1 particle in the first remote band and 0 particle in the second remote band. And you see that as soon as you allow particles to go into the second remote band, the threefold degeneracy will change. So, and for a fractional translators, the momentum sectors for the 3 low energy states is a signature that you can deduce from the nature of the phase. So having the quantum numbers of 3 low energy states changing from here to here is already a sign that the FCI is gone. Actually, you can show that in this case, this should be related to a gapless phase. So under band mixing in the weak Moire regime, the FCI is killed. Now we can do the same in the strong Moire regime using the average scheme for the interaction. So the top part here, you have what's going on at 2/3. And you see that at the beginning, the FCI is not great if you have a strong Moire. This will be improved when you increase the band mixing. but at some point it will die out. For 1/3, the situation is even worse because the FCI is quickly killed under band mixing. So that's a summary, for example, of the gap above the FCI for different system sizes as a function of the truncation, so the number of particles that you allow in the first remote band over the total number of particles. And as you can see, there is always almost a collapse of the FCI. So the outcome of this calculation is, using the model and reasonable parameters, we are not able to stabilize any FCI as soon as you move away from the approximation of working with a single band. So, this leads to the question, can't we be nicer? Especially with the FCIs. So a fair concern. We know that we have lots of finite size effect. We know it already from the Hartree-Fock calculation. So maybe the reason why band mixing kills the FCI is, well, the correlation length is a bit bigger. So in that case, you need to reach really bigger system sizes to stabilize an FCI potentially. But unfortunately, we don't have unlimited computing resources. And so we cannot keep the 3 bands and do a large enough system size calculation. Once again, what we do here is just a basis transformation and should be really equivalent if we don't have any truncation. So the idea could be, well, okay, you use the Hartree-Fock basis to do your perturbation scheme, but could you choose another one-body basis, like equivalent created by unity transformation, but where the convergence toward the FCI would be faster? So, of course, since at the end of the day you have to perform a many-body quantum calculation, this kind of optimization cannot be done in a brute force way, just by exploring all the possible unity transformation acting on the one-body basis. So we need basically some physical insight to choose this optimal one-body basis. So one way we propose to deal with this question is the following. Let's start with the original Hamiltonian and we apply some truncation. Let's do a full ED calculation. And now for the 3-state, we can compute a density matrix. And the density matrix will give you eigenvalues. We'll have eigenvalues at each k point, which is basically what is pictured here. And we can use that as a way to redefine our one-body basis, where we will maximize the weight on, let's say, one of the eigenstates of rho of k. We then perform a transformation based on the eigenstate of rho of k to obtain new creation annihilation operators and get a new Hamiltonian, and you can just repeat the operation and hope that at some point this would converge. So you might wonder, why would that work? Well, at least if you work with product states, this will work. This will give you a transformation that bring your system into a single band. It has pretty nice features such like we can define a convergence criteria based on the eigenvalues of the density matrix. Now, it's may almost always converge, but you can build identical counterexamples. So it's not, a procedure that is guaranteed to converge, but most of the interesting cases, it works. And it only requires a few tens iterations. That's an example where we look at the evolution of the occupation of the band with the highest weight. And we can compare to the overlap with the state at 1/3. But basically, you see that after a few iterations, you have conversion. But note that you don't change much the occupation. So does that work? This is for the 1/3 state with the weak Moire. So let's forget about the details of all these plots here. The thing is, what you can show is, well, the iteration reduces the band mixing, which is good, which is what we're looking for, like a basis where we have almost everything in one band. But it's not a major improvement. But the thing is, if there's an FCI without band mixing, as soon as you have some band mixing, the FCI will turn into just Charlesty wave. So in any case, whatever you do, the FCI disappear at 1/3 in the weak Moire regime, even if you try to optimize the one-body basis. For 2/3, with a strong Moire regime, it's once again the same story that the one I've shown previously. So this iteration will happen a little bit. It's slightly affect the band mixing, but not by much. And to some extent, you stabilize a bit more the FCI, but you don't save it. So as soon as you crank up the band mixing, the FCI will just disappear. So it's pretty depressing. And we might wonder, okay, what should we do to get an FCI? So if you look back at the continuum model, that I didn't provide you the formulation here, but basically more or less you have 12 parameters. And remember that each time you do a quantum many calculation, it's something that can take like several hours to several days to get the result. So there is no way we can perform a full scan of the parameter space to try to find a region that is stable under band mixing. So can we try to devise some criterion based on a simpler calculation, typically like a Hartree-Fock calculation, that will allow us to pinpoint a region where we might get a stable FCI under band mixing. When you're dealing with an isolated band, basically what you will try to do with the parameters is to optimize the flatness of the band while keeping the Chern number equal to 1. But it's not the case for rhomboidal. It's not a single isolated band. So because here you have almost bands are almost degenerate. So the idea that we had is the following: we can try to, if you look at the Hartree-Fock results and the Hartree-Fock spectrum, what you will get is try to look at the charge excitation, and you want to have something which is different from a Fermi liquid. So basically to have flat charge excitations. And that's something that, for example, you can tune the displacement field to improve the situation. And the other part is basically to use time-dependent Hartree-Fock to look at the stability of the Chern 1 band. And one important parameter here that will help to stabilize the Hartree-Fock band is the Moire capacitor effect. So basically what I was mentioning, the fact that the valence band imprint the Moire the Moire potential on the conduction band state. So with that, we have found maybe a nice region. So let's try to give it a try. Let's give it a try and see if we can stabilize an FCI. Unfortunately, there's already a question like, we need to take a system which is large enough, because we know that if the system is too small, we might be in a situation where we don't see an FCI because the system is too small. So 21 unit cells, which for 2/3 should be equal to 14 particles.
Nicolas,
just
to let you know, 5 minutes to 40. Yeah, thank you. So you have, it's pretty much the sweet spot. Even though if you were doing the full diagonalization without band truncation, the Hilbert space will be more than what you can do on any supercomputer on Earth. And we will use two types of truncation. Like previously, we will, for example, here cap the number of particles we have in the remote band. And we will also remove some of the states which are too high in energy. So here I plot the single particle state for their energies as a function just by sorting them by energies. The black dots are the lowest conduction band, orange the first remote band, blue the second remote band. And you can see that we can exclude some of these points which are too high. So if we just allow for particles in the first remote band, now you see here that the gap of the FCI seems to converge to a finite value. So I think that's the first example where we can include band mixing, actually cranking up to the max, and still get a stable FCI. So is it done? Well, no, because as soon as you include the third band, or the second remote band, then here your gap once again collapses. And that's a message, especially for the young people that will want to do that kind of work. Sometimes don't try to optimize the target parameters. So what we did was try to optimize the FCI gap in a small region of the parameter space. And then push the calculation by including more and more states or to decrease the truncation parameters. It doesn't work out. So let's give a second try. And this time what we want to do is basically, since we know the third band is the one killing our state, let's tune the parameters slightly to push up the second remote band. And we can play the same game of excluding some of the states which are too high in energy and so on. So particles in the first remote band, the gap seems to converge, like we did previously. And now these are the results with the third band. We're still running some calculation at the moment to be sure that it will not collapse, but at least for the time being, everything seems to work fine. And really, a message here: it's truly a three-band FCI. In a sense, if you look at the density matrix, if you look at the eigenvalues, it's not like one eigenvalue is maximal and two others are very small. Of course, there is a dominant one, but the two others are not, on the order of 0.1, 0.2. So meaning that it's inherently a three-band system, and there is no way to bring it to a single band problem. So in the last 2 minutes, just to advertise some work about, what about the Moire? All the beauty of Moire materials, and we have somehow only scratched the surface, because if you look, we basically have graphene and TMDs. But what about other lattices and other systems? And the idea of finding better materials or showing different physics. So for people that are interested in, we have two recent papers. One about a new database for 2D materials, where you can find all the information about the band structure, the topological properties, and so on, for more than 8,000 entries. Also, we did the work of tagging materials that have been realized experimentally, and sometimes even with the reference to the right paper, which is kind of useful. And there's also a way to determine which one are theoretically twistable, and it can lead to some interesting physics. And we have several candidates for semimetals and more than 1,000 candidates for twistable insulators. All right. So in conclusion, once again, FCIs are a very exciting topic. It's definitely richer than fractional quantum Moore effect. But sometimes it's more complicated than the naive picture of, a band, a non-trivial band with strong interaction. And clearly, pentalayer graphene is one example of the difficulty that you have when you try to look at realistic system. And as been confirmed by more recent experiments, the Moire due to the HBN is really important. So if you don't have it, you don't get any FCI, and that's in line with what we observe in the numerical simulations. And at that time, we clearly don't have any
explanation based on a single band model, as soon as you have band mixing, the FCI disappear. And the latest result I've shown you that are still unpublished tends to show that if we have an FCI there, it's definitely not a single band FCI.
So the image froze. I don't know if he ended the talk. Nicolas, can you hear us? Did we lose connection? Okay.
Can you hear me?
Yeah, I can hear you now, but the image froze for a second. So have you finished, I think?
Yeah, I'm done. Thank you.
Yeah, let's thank Nicolas for the presentation. So the presentation is open for questions. Please raise your hand and I'll bring a microphone to you. Buddy.
Hi, Nicolas.
Hi. Happy birthday!
Thank you very much. Sorry for not seeing you here. Is the composite family liquid the problem easier or harder to deal with by exact generalization? So the transition from a Fermi liquid to a CFL to a composite Fermi liquid, is this something that can be looked at numerically?
I wish, but even to get a very clean CFL in twisted MOTE2 is not easy. So CFL, the way it's a gapless system. So in principle, it's going to be worse. But the good thing is we have, even in finite size, we have many ways to identify a CFL. So that's my hope. It's not completely hopeless to deal with the CFL in either ED or D emoji.
But it's not something you looked at.
We have some unpublished results on twisted MOTE2. And that's the problem. It's hard to have very clean CFL signature there, even though it's simpler model that's in Pentalayer.
Thanks.
Okay, some more, yeah.
Hi. Can I think about this iterative procedure as some kind of RG procedure, and which indicates that the FCIs are unstable in the closed regime, and within this set of Hamiltonians, you have to really fine-tune the parameters to get to the fixed point. Otherwise, you flow away to the other regimes.
I mean, that's what you could say, because it's, each time there is a truncation involving the process. So of course, it wouldn't be RG if you were doing the calculation without any truncation, because it just, once again, it's just unitary transformation, so the iteration will stop immediately. So basically, you try to have an effective model which uses single band. But I mean, as I was honestly showing, it does not converge every time, the procedure itself. And at the end of the day, we have never found any case where it stabilized the FCI. It could be that we are looking at some this iteration based on the density matrix might not be the optimal choice when it comes to the transformation. But once again, there is no way we can do an actual optimization procedure on the full space, the full set of unitary transformation.
So any more questions? While people think maybe can ask one. So is it a fair thing to say that if I were to extract out as a summary of the talk on the FCI, that you would say that there's a minimum at least of 3 bands that are needed in order to produce an FCI state? If you're stuck with 1, you don't get it. If you get 2, you don't get it. 3 is minimum. Or is, if you haven't tried 4, 5, what happens with the FCI if you have tried that or not? Or is an optimal number?
No. The thing is, if you have a single band, the question is which band you use.
Right.
If you look at what people did in like 1 year ago, they used one band that they extract from the Hartree-Fock calculation, which, you're basically using a band that you get by interaction, and now you put once again interaction on top. So it's a very risky business. And you get an FCI. Actually, you get FCI almost everywhere. But once again, getting FCI in one band setup is not surprising.
Right.
I mean, of course, you can find cases where it's not there, but most of the time it will emerge. So the problem here is the exact opposite. It's like, adding bands will destabilize, will kill your state almost immediately. And that's what we are trying to do, to try at least in a 3-band setup, because 3-band is like the bare minimum. If you look at the dispersion of the conduction band, it's most gapless for these 3 bands. So of course, if I was super rich, I would have 4 or 5 bands. But the band that we can do numerically at the moment, either within exact organization or DMG, is 3 bands.
Okay.
And I don't see how we're going to include more. Just limitation of resources.
Any more questions that we like to ask? Yes, no? Okay, so then let's thank Nicolas again for the talk. And I think
and sorry for being away again.
Oh,
I wish